Okay, so today we are going to look at a simple application of the projection operator. The projection operator method in this context is something that is used to construct suitable basis functions. Okay. Now, we will take an example of this. The problem statement here is that construct basis functions for 2D representation of group D3 starting with an arbitrary function xy plus yz plus xz using projection operators. Okay. So, our goal is to start with this arbitrary function, okay, and assume for now that we do not know what a suitable basis for this two dimensional representation is. Okay. So, you have no idea, assume that you do not know what a suitable basis is. Okay. So, then how do you use projection operators to construct the appropriate basis functions? Okay. And this is the application of this is an illustration of the projection operator method, and you can use this method to actually to decide later on which are the suitable linear combinations to use. Okay. So let us remind ourselves what this group D3 is. So D3 has is a group of order 6. It has identity, it has C3 and C3 square and 3 C2 axis. So this is if we align the C3 axis along the Z axis, one of the C2 axis we align along the X axis, the other two are in the XY plane. Okay, the other two C2 axes are in the XY plane, and this angle between them is 120 degrees. Okay. So these are the various elements of this group. These are the various classes, and you can easily work out using the great orthogonality theorem that you can work out that there should be three irreducible representations, two one-dimensional irreducible representation and one two-dimensional irreducible representation, and then you can also work out that these should be the characters. Okay. So let us say we know this much about the group, and now what we want to do is to find out what are suitable basis functions for 2D representation, okay, starting with this arbitrary function. Okay. Now we already know that x and y form a basis, okay, as do Rx and Ry. Okay. Now what we are looking at is suitable products that form such basis. Okay. In order to do this, we need to write the appropriate projection operators and see what they give. Okay. So we'll use this technique. We will project out. So we want to project in the representation. So this is the representation. Okay. So we want to construct an operator that is characteristic to the representation, and we always have two indices here. So let us work out the diagonal elements. So we can work out the 1 1 and P 2 2. Okay. And what we will show is that these two are sufficient to derive to get two basis functions. Okay. So we are looking at the 1 1 projection. Okay. We are looking at the 1 1 projection operator and the 2 2 projection operator. Okay. So now let us and what we are going to do is we are going to write these operators and operate them on this quantity xy plus yz and plus xz, and that will immediately give us two orthogonal a two-dimensional representation for this irreducible representation. Okay. So will give us two basis functions. Okay. So let's start following the procedure. Now in order to do this, we need the matrix elements. So need matrix elements of all operators in 2D representation. E. Okay, so we need the matrix elements of all the operators in this 2D representation E, and you can work out that in this 2D representation E, this E should not be confused with this E. Okay, this is the representation E, this is the identity. Identity is always the diagonal matrix. Okay, since it's a 2-dimensional representation, it will have 1 1 0 0. Then you can work out C3. C3 will have this representation minus half minus half. Okay, so and you can work this out by actually calculating the matrix elements in the 3D representation and then breaking up the 3D representation into a 2-dimensional and a 1-dimensional representation. Okay, so you can work out C3, C3 square, C2, C2 prime. C2 is, since it's along the x axis. Okay, we can work this out. So C2, C2 prime and C2 double prime. Okay, so these are the various matrix elements. Notice that the character of E is 2, which is here. Character of C3 is -1. Character of C3 square is -1, and both these are here. Character of C2 is 0. C2 prime is 0 and C2 double prime is 0, and that is here. Okay, so this is a valid 2D representation of this this is a valid 2D matrix representation of E. Okay, so we need these matrix elements, and then we need to construct the appropriate projection operators. So the way to construct the projection operator, okay, and let's remind ourselves. Yeah. So if we want P E I J, okay, then we calculate this by L L of E. Okay, that is the dimension of E divided by H. Okay, so for any representation, the dimension of that representation divided by H. Okay, and then what you have is sum over all operations of the group. Okay, then you look at the matrix element in this representation of R, and you look at the ijth element. Okay, and you take a complex conjugate, and you look at R, multiply by R. So this is our projection operator. This projects onto this this ijth element. Okay. Now suppose you want to calculate PE 11, then what you need is LE is 2, H is 6, okay, and then what you have is sum over R or all the operations. You need gamma, you need the matrix element of the operation, and you need the 1/1th matrix element. Okay, so you need the 1/1 element of the matrix. Take a complex conjugate and multiply by R. Okay, now the 1/1 each the 1/1 elements of these matrices are 1 minus half minus half, 1 minus half minus half. Okay, so those are the 1/1 elements. Okay, so we have this part. This part is something we have quite easily. Now the question is, what do we choose for R? Okay, now so for R we will put each of the operations. We will put each of the operations, and when you operate on any function, we need to know how that R operates on the function. Okay, so just say here, to find P E 11 on any function, we need R operated on any function. Okay, so if you want to know how PE acts on any function, you need to know how R acts on any function. Okay, so this we have to say what is E acting on the function is xy plus yz plus xz. Okay, so when E operates on this, Now E is the identity element, so when it operates on it you will just get the same thing. Now how do you know what happens when C3 operates on this function? Okay. In order to find out what happens when C3 operates on this function, you need to know what happens when C3 operates on X. Okay. So if you know what happens when C3 operates on X, Y and Z independently, then you can calculate what happens when C3 operates on this function. Okay. Similarly for C3 square, for C2, C2 prime and C2 double prime. So you just need to know how these functions act on the coordinates. Okay. Now you can immediately see this when C3 acts on X. Okay, when C3 acts on X, it will give you minus half X plus root 3 by 2 Y. Okay, that is what it gives you. Okay. When C3 acts on Y, you get, so when C3 operator on X gives you this, C3 operator on Y gives you, you can see from here it is minus root 3 by 2 X plus or minus Y by 2. Okay. When C3 operates on Z, you just get Z. Okay. So what we have seen is, we have seen what happens when C3 operates on X, Y and Z. So now you can calculate what happens when C3 operates on X square or XY plus YZ plus XZ. So when C3 operates on this, what you get is you'll get, so X into Y, so it is product of these two, Y into Z will be product of these two, and X into Z will be product of these two, and I will write the total expression. So the total expression that you will get root 3 by 4 into X square minus Y square minus XY by 2 minus 1 plus root 3 by 2 XZ minus 1 minus root 3 by 2 YZ. Okay, so you can take all these products and you can verify that this indeed is the expression. Okay, so this was an illustration, but you can easily see that you can do the same thing for each of the other operations. So you have to do this for all the other operations. Okay, you have to find out how C3 square operates on this. Okay, so similarly for C3 square, C2, C2 prime, C2 double prime. Okay, so you have to find how all these operations act on XY plus YZ plus XZ. Okay, so each of them will give you some big function. Okay, and what you have to do is, this is what your R of phi is. Okay, so you have all the expressions for R of phi, and now you can combine this to calculate your PE11. Okay, so let's go ahead and do that. So what we have is PE11 is equal to, so you have 2 by 6 times. Okay, now you have 6 terms corresponding to each of the 6 operations. Now the first everything is pre-multiplied by gamma 11 star. So for identity you have 1 into the effect of identity on this operation. So should rewrite it. I should write this as PE operated on XY plus YZ plus XZ. Okay, so this is equal to, so you have 2 by 6 into, you have sum of various terms, and so the first term is just 1 into xy plus yz plus xz, because the identity operated on xy plus yz plus xz just gives itself. Okay. Plus now for C3 we will do for C3. So, for C3 the 1 1 matrix element is minus half. So, you have minus half, okay. And now when C3 operates on this, you get this whole thing, okay. So, into root 3 by 4 x square minus y square minus x y by 2 minus 1 plus root 3 by 2 x z minus 1 minus root 3 by 2 y z. Okay, so, all this is multiplying minus half, and then similarly you will have for C3 square. So, you will have minus half into again sum of various terms. Then you will have for C2, you will have for C2 the 1 1 element is 1. So, plus 1 into this is C3 square operated on xy plus yz plus xz. This is C2 operator on xy plus yz plus xz, okay, and so on and so on. Okay, so, you have these 6 terms and you have to collect all of them together. Okay. When you collect all of them together, what you will find is you will get some function, okay, and that function is what will tell you what is the 1 1 projection of this function, okay. And if you work out the whole thing, what you will get is that if you look at all the terms. So, you have terms like x square minus y square, terms like xy, terms like xz, yz, okay, and you collect all the terms together, okay, and you will get a very simple looking expression. Everything else will cancel. All you will be left with is xz, okay. So, PE11 will just give you xz. So, the projection of this onto the 1 1 matrix element is just xz. So, what we get is PE 1 1 of x on xy plus yz plus xz is equal to xz. Okay. Now, the same thing can be repeated for PE 2 2. Okay. So, the 2 2 element and everything will look identical, will look almost the same, only thing instead of using the 1 1 matrix element, you will use the 2 2 matrix element. So, it will be 1 minus half minus 1 half half. Okay. So, these 3 will be the same, these 3 will change sign, okay. And when you calculate this, when you put all that together and calculate this, you will get is equal to yz. Okay. So, just using PE11 and PE22, we constructed two basis functions xz and yz. Okay. So, PE projects, so PE11 projects this, okay, onto this collects a diagonal projection of this, and that is xz. Similarly, this collects another diagonal projection, that is yz. Okay. And so this implies yz form a basis for E. Okay. And you can indeed show that this suitable basis is xz, yz. In fact, there is another basis that can also be got from this projections, okay, which is x square minus y square xy. Okay, so there were terms involving x square minus y square and xy. Okay, and they can also, it can be shown that they also form a basis. Okay, so using this projection operators, you can find suitable basis for for the two-dimensional representation. So what we have seen is that x z and y z, you can, from starting with an arbitrary function, we found a suitable basis for this two-dimensional representation, and you can actually work out lot more basis functions using this projection operator method. I won't go into the details of that, but you are encouraged to try out and generate some of the other basis functions. Okay, so what you'll find is that if you start with x y, you'll be taken to a mixture of x square minus y square and x y. So that's how you generate the other two basis functions. Well, so the point is, this method can be used to actually get a suitable basis. Now what I want to point out is that this method is extremely tedious, because we have to construct the matrix elements of each of these operations. Okay, now that itself is a tedious process. For a two-dimensional representation, constructing matrix elements is not that easy. For one-dimensional representation, the matrix element is just a scalar, and that is just the character. Okay, but for two-dimensional representation, the character table has characters, but then you have to take the characters and you have to identify the suitable two-dimensional representation, and you can imagine that for a three-dimensional representation it would be even more difficult. Okay, so you have to calculate, you have to have all these matrix elements, only then you can construct suitable projections. So there is so the question is, can one use only chi of r instead of chi e of r instead of gamma e of r I j I, okay, the diagonal elements. Okay, so instead of using all the elements, we just want to use a trace. Okay, the answer is that no, that is not sufficient, but you can get by in some cases. Okay, so in principle, chi e of r, okay, this is for two-dimensional and three-dimensional representations, is not sufficient. Okay, but we can manage in practice. Okay, so what I mean is that formally, if you think the trace contains much less information than the actual values of the matrix elements. So the trace of C2, character of C2 is 0. Okay, character of C2 prime is also 0, character of C2 double prime is also 0, but then their matrix elements are very different. Okay, so and it's important, and you saw that for the projection operator we need to actually know the matrix elements. Now the question is, can we get by using this trace? Okay, and let's see what happens. So we construct PE. Okay, construct PE is equal to PE 11 plus PE 22. Okay, so we are just summing over all the diagonal elements. So if you had a three-dimensional representation, then you will sum over all the three diagonal elements. Okay, so now this is equal to sum over R, okay, Li by H, sum over R, and what you have is gamma sum over R and L E, okay, gamma E of R ith element. Okay, and what you have is a sum over I. Okay, sum over all the diagonal elements. Okay, star r. Okay. And what you can do is you can interchange the order of the sum over I and the sum over r, and you can show that this is nothing but Le by H, okay. Sum over r, what you have is chi E of r star r hat. Okay. So now you only need the trace, you do not need the individual matrix elements. Okay. You only need the trace, but you do not need the individual matrix elements. Unfortunately, you still need to know how these matrix elements operate on the arbitrary function. So how you still need to know r operated on this, okay. But what we will see is that turns out to be much easier to calculate, okay. And you can show you still need to know all these, in a sense you still need to know all these, okay, for all the operations. However, it will turn out to be a lot easier to calculate, because in some cases you just need the sum of C2 prime and C2 double prime, okay. So you just need the sum of these three, and that in general is easier to calculate, okay. So you can show this is called the incomplete projection operators. This quantity is called the incomplete projection operator, okay. And using the incomplete projection operator, can we construct a suitable basis? And the answer is in some cases yes, you can, okay. Okay, so can we construct basis functions using PE hats? And what you will show is that PE hat operated on xy plus yz plus xz, this will turn out to be just xz plus yz. Okay, this is just xz plus yz because it is just the sum of these two operations. Okay, so what we get is you get a function, and at this point you do not know that xz and yz they together form a basis. Okay, you just have this combination of xz and yz, and it takes a little bit more work to actually show that the two functions xz and yz are the functions that form a basis. Okay, so basically this gives a function which is a sum of basis functions. Okay, so it gives something which is a sum of basis functions. And in principle you can break this into two functions in many different ways, okay. But so it does not uniquely give basis functions, okay. Now it does not uniquely give basis functions. So can you take this and show that indeed this is composed of those two basis functions? And the answer is usually you can do this, okay. You need to use some other techniques, okay. Let us now use the procedure of symmetry adapted linear combinations and show how we can, using the projection operators, how we can construct some symmetric linear combinations, some symmetry adapted linear combinations, okay. The first example I will do is a fairly straightforward example. This is consider the molecule ethylene molecule. Okay, so it's a planar molecule, one double bond, so C2H4. This molecule, so in ethylene, construct SALCs using s orbitals on H atoms. Okay, so using the 4 s orbitals on the 4 H atoms, on the 4 hydrogen atoms, let us construct some symmetry adapted linear combinations. Okay, now now a few things you should know. First is that the s orbital, okay, is located on these 4 hydrogens. So the geometry of ethylene is it's a planar molecule. Okay, it is perpendicular to the plane of the board. We will choose our axis so that along the CC bond is the x direction, this is the z direction, and in the plane of the molecule is the xy plane. Okay, now this molecule belongs to point group D2H. Okay, D2H has 8 operations. Okay, they are E. There is a C2 axis, so x axis is a C2 axis, as is the y axis and the z axis. So there are 3 C2 axes. Okay, this is C2z, y, and x, and then there is a center of inversion. So you can take this and you can invert it about. Okay, so you will get it has a center of inversion. It has 3 sigma planes. So each of the xy plane, the xz plane, and the yz plane, they are all planes of symmetry. Okay, so now if you work out the classes, it will turn out that there are 8 classes. Okay, there are 8 symmetry operations and 8 classes. Okay, since there are 8 classes, there have to be 8 irreducible representations, and each of them has to be a one-dimensional representation. So there are 8 one-dimensional irreducible representations denoted by AG, B1G, B2G, B3G, and then AU, B1U, B2U, B3U. Okay, and I've reproduced the character table. Okay, just a point to note, if you notice in AG there is 1 1 1 1 1 1 1 1, in AU it is 1 1 1 1 and -1 -1 -1 -1. So if you take any of the G representations, okay, it will be symmetric. The first 4 and the next 4 will be the same. Okay, so for example, you have 1 -1 -1 1 1 -1 -1 1. Okay, whereas if you take the corresponding Ungerad representation, U representation, you will have 1 -1 -1 1 as it was, but then these ones have changed sign. So it is -1 1 1 -1. So now let's construct SALCs using the s orbitals on hydrogen atom. Okay, I am going to call these as follows. I will call this s orbital sigma 1, this sigma 2, sigma 3, sigma 4. I will just call these sigma 1, sigma 2, sigma 3, sigma 4. And now you ask a question, if I take this sigma 1, if I perform a C2 operation, let's say C2y operation, if I perform a C2y operation, what will happen to sigma 1? So if I perform a C2y operation, you can see that rotate about the y axis, so sigma 1 will become sigma 4. Okay, so and you can do this for all the 4 orbitals, all the 4 s orbitals. So if you do C2 about the y axis on, let's write sigma 1, sigma 2, sigma 3, sigma 4. Okay, then what you get is the following: sigma 1 goes to, so C2 means this will go to sigma 4, sigma 1 will go to sigma 4, sigma 2 will go to sigma 3, sigma 3 will go to sigma 2, sigma 4 will come to sigma 1. Okay, it is not hard to show. Okay, now this I can write as 0 0 0 1 0 0 1 0 0 1 0 0 1 0 0 0 times okay. So I can write this in this form, and so this becomes a 4-dimensional representation for C2 of y. Okay, so this is the matrix corresponding to a 4-dimensional representation of for C2y, and chi of C2 y equal to 0. Okay. Now you can see that you take chi of any other operation. So for example, if you take chi of C2z, C2x, okay, you'll again get 0. Okay. So the chi's for all these operations will be exactly equal to 0. Okay, and you'll find that only 2 of the chi's are non-zero. Okay, only 2 of the chi's are non-zero, and they are they correspond to E and I. Okay, so all chi's are 0 except chi of E, and chi of E, since it's a 4-dimensional representation, you have to have 1 along the diagonals. Chi of E equal to 4, and chi of I, okay, so not chi of I, and chi of sigma xy. So the molecule is in the xy plane, so chi of sigma xy, okay, this is equal to 4. Okay, so if you do a sigma operation, if you reflect about the xy plane, then sigma 1 stays sigma 1, sigma 2 stays sigma 2, all these remain as they are. Okay, and these two have non-zero characters, everything else has character 0. Okay, so this is what we can use to easily now starting with this we can easily construct various combinations. Okay, so let's look at the projection. Okay, so we can look at projection onto okay, so before we do that, we can do one thing. So in this representation, this is a reducible representation where all the characters are 0 except character of identity and character of sigma xy. So you can ask a question, how many times does AG appear, how many times B1G appears, how many times B2G appears, etc. So you can ask how many times each of these representations appear in this irreducible representation, and it's not hard to see. You can see that you can just look at it and you can immediately see that so B1G where is sigma xy? Sigma xy, yes. So AG, B1G, B2U, B3U. So you can see the, or you can take B2G, B3G, AU and B1U. So you can take those 4 and they appear exactly once. So you can write this in 2 different ways. So oh no, okay, so this is 4. So you can see that if you want 4 here, so you have to take this and this. So this representation, so this representation can be reduced. So 4D representation is equal to AG plus B1G plus B2U plus B3U. Okay, so just to confirm, if I take these two, add them up, then I'll get 2 here, 2 here, 0 0, 2 here, 2 here, 0 0. Okay, so then if I add these two, then I'll get 2 here minus 2 here, which will cancel this 2. So we'll get 4 0 0 0 4, no, this is 0 4 0 0. Okay, so that's what I'll get. So which is exactly the same as these characters. Okay, so this 4D representation can be written as AG plus B1G plus B2U plus B3U. So now if you want to, so that means these are the only representations, okay, that will have non-zero projections. So these are the representations that will have non-zero projections of this basis. So you can take you can calculate projection in AG irreducible representation of and since there is only one element, okay, this is a one dimensional irreducible representation, there is only one element, okay, so we'll calculate the projection operator in AG, okay, and this you can show, this is sigma 1 plus sigma 2, or this operated on sigma 1 plus sigma 2 plus sigma 3 plus sigma 4, this is just sigma 1 plus 4. Okay, I am not bothering writing the prefactor, the Li by h 1 by 8 factors, so they will be constant, so I won't bother to write that, but basically this will just be sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay. Similarly, projection operator of B1G of sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay, and this you can directly see, this will in this case the character here is 1, okay, so you will always have sigma 1, okay, the character of sigma xy is 1, so you will still have sigma, so you will have sigma 1, yeah. So so this will look like sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. Okay. So the way to do this is you have to look at how each operation acts on these sigmas, okay, and then you can work out this is a projection operator, and then you can work out the remaining two projection operators. P, I'll write it in slightly shorter form, B2U equal to this, P B3U is equal to this. So this is sigma 1 minus sigma 2 minus sigma 3 plus sigma 4, and this is sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. Okay. So the point is we can work out all these projection operators, and so these are the four. So when you take sigma 1 plus sigma 2 plus sigma 3 sigma 4, you project it onto the AG irreducible representation. That projection is just itself. If you project it onto B1G, you will get this, okay, you will get sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. If you project it onto B2U, you will get this, and if you project it onto B3U, you will get this. So these are the four symmetry adapted linear combinations that you can construct, 4 SALCs from. So these are the four symmetry adapted linear combinations that we constructed from sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay. So this is this completes this exercise of how to construct SALCs using the s orbitals of hydrogen atom. Okay. Now the next exercise is slightly more tricky. This involves a two-dimensional representation. So let's consider PtCl4, okay, platinum PtCl4 2 minus. Okay. Now this so PtCl4 2 minus has the PtCl4 unit is planar, okay, so it is planar and this belongs to point group D4H, okay, this belongs to point group D4H, okay. Now D4H has 16 operations and it has 10 classes. So 16 operations and 10 classes. So there are 10 irreducible representations. Okay, there are 10 irreducible representations, and now we will focus on one irreducible representation, which is a 2-dimensional representation EU. Okay, and what we want to do is the same thing we did last time. We want to construct suitable basis for EU using sigma 1, sigma 2, sigma 3, and sigma 4. Okay, so we'll use the four orbitals, okay, of sigma 1, sigma 2, sigma 3, and sigma 4, and we'll construct a suitable basis for EU. Okay, so let's do this in a we'll do this in a very instead of going through the whole laborious procedure. So I'll just mention what we want to do is construct a basis for EU starting from 4 orbitals on PT. Okay, so the four orbitals connected to PT. Okay, so let's PT2 plus. Okay. Sigma 1. Okay, so let's in order to do this, we'll just use this coordinate system where the x-axis goes along one of the CL, the y-axis goes along the other CL, and the z-axis is perpendicular to the plane of the molecule. So now let's look at sigma 1. Okay, now if you operate so in this case, okay, and what you want to do is to give the result of all the operations on sigma 1. So clearly E of sigma 1 equal to 1, okay, and then you have C4. Well, we don't care about C4. Let's look at C2. Okay, so in order to find the projection operators, you need to know how each operation acts on sigma 1. Now if the character of the representation is 0, okay, then you know that it won't contribute to the projection operator. Okay, so we are going to use the incomplete projection operators. So if the character is 0, then we will say that anyway, since it doesn't contribute to the projection operator, I don't need to bother how C4 acts on sigma 1. Okay, so I'll just see how C2 acts on sigma 1. So so when the identity operates on sigma 1, you just get sigma 1. Okay. When C2 has a non-zero character, okay, when this operates on sigma 1, okay, now C2 when it operates on say sigma 1, okay, we choose C2, so it takes it to sigma 3. So C2 operated on sigma 1 is sigma 3. Okay, so C2 is will take sigma 1 to sigma 3. Okay, C2 is like rotation by 90 degrees about the z axis, rotation by 180 degrees about the z axis. So sigma 1 will come all the way to sigma 3. Okay. What about I? The inversion operation, when it acts on sigma 1, will give you sigma 3, and similarly when sigma h operates on sigma 1, you will get sigma 1. Okay, so the projection operator, the projection operator on EU, okay, projection onto EU of sigma 1, okay, can be written using the incomplete projection operator. This can be written as sigma 1 times character of E. Character of E is 2 plus sigma 3 times character of C2. Character of C2 is minus 2 plus sigma 3 times character of I is minus 2, and sigma 1 times character of sigma h is 2. Okay, so then this is just twice sigma 1 minus sigma 3. Okay, so therefore we can immediately say that sigma 1 minus sigma 3 is a basis. Okay, so sigma 1 minus sigma 3 is a basis for this for EU. Sigma 1 minus sigma 3 is a basis for EU. Is sigma 3 is one of the basis functions for EU. Okay. Now to construct other bases, so in principle, if you want to construct the other bases, you will need the other matrix element. So we worked with the incomplete projection operator. So we used only the character. We used only the characters, but we will need the full matrix elements. But actually, we can do it in another way. We can do it in another way, and to do this, what we will see is that we take sigma 1 minus sigma 3. Okay, you take sigma 1 minus sigma 3. If you operate it by all these 10 classes, okay, you operate it by members of all the 10 classes. Okay, actually you have to operate it by all the 16 elements. Okay, and you look at what you end up with in each case. Okay, now if you operate it by E, if you operate sigma 1 minus sigma 3 by E, you will end up with sigma 1 minus sigma 3. So clearly, so R of sigma 1 minus sigma 3 equal to plus minus sigma 1 minus sigma 3 if R is equal to, R is contained in E C2 C2 double prime, no sorry, E C2 I sigma h. Okay, so these operations, these 4 operations will give you exactly sigma 1 minus sigma 3. Okay, now this is very obvious, because these are the operations that have non-zero projections. So in order to find the other bases, we can use one trick. We can operate on sigma 1 minus sigma 3 by some other operation. Okay, so let us operate by an operation that does not belong to this set. So let us operate by C4. So C4 operated on sigma 1 minus sigma 3. Okay. Okay, so C4 will take sigma 1. C4 will take sigma 1 to sigma 2. Okay, so it will take sigma 1 to sigma 2, and it will take sigma 3 to sigma 4. So now you can immediately look at this, and you can say that probably C2 minus C4 will be a other basis function. Okay, so this implies sigma 2 minus sigma 4 is other basis function. Okay, we can just guess this. Okay, just guess this based on the fact that C4 takes it onto this. Okay, and sure enough, if you look at sigma 2 minus sigma 4, then when it acts on identity, so this is easily verified. Okay, easily verified, because when you operate it by identity, you will get sigma 2 minus sigma 4. When you operate it by C2, you will get minus sigma 2 minus sigma 4, when you operate it by I, you will get minus sigma 2 minus sigma 4. When you operate it by sigma h, you will get sigma 2 minus sigma 4. Okay, so clearly this is the other basis function. Okay, so so without doing too many calculations, we were able to arrive at these two basis functions. Okay, we use some logic here, in the sense that we started with a sigma 1 and we ended up with sigma 1 minus sigma 3. So we guessed that sigma 1 minus sigma 1 minus sigma 3 has to be a basis. Okay, then what we did is we looked at how the operations, so clearly C4, when it operates on sigma 1 minus sigma 3, gave something that is orthogonal to sigma 1 minus sigma 3. Okay, and so that we guess this, and then we can easily verify that sigma 2 minus sigma 4 is another basis for this representation.